Hello everyone, myself Tanya. I am pursuing my software engineering degree from Chitkara University. Today, in this video, I am going to discuss about the design and implementation of the Hack CPU as a part of my 9.3D task. So to begin with, the CPU consists of various logic gates such as the ALU, A register, D register, multiplexer, etc. Since we have already learned to build almost all of the above said gates in the previous tasks, it would now be easier to understand the HDL code for the Hack CPU. There are three inputs coming into the CPU from different sources in the computer as shown in the diagram. These inputs are namely instruction, enum, and reset. Instruction input comes from the instruction memory. This instruction can either be an A instruction or a C instruction. Now let me brief you about both of these instructions. The symbolic syntax for A instruction is @value, where value is either a non-negative decimal constant or a symbol referring to such a constant. Moving further to the C instruction, the symbolic syntax is destination is equal to computation and jump. The binary syntax for C instruction is as shown in the slide. There are various tables that help us to understand more about computation, destination, and jump. Coming back to the inputs again. Input enum is the value of the currently selected data register and is the value that the CPU needs to perform various operations. The CPU is connected to the instruction and data memory respectively. The CPU takes its instruction input from the instruction memory and also takes the selected data memory register as one of its inputs. The reset input is a value that tells whether we brought the CPU back into its initial or starting state. Further, the CPU has four outputs that are connected to the instruction and data memory. These outputs are outem, writem, addressem, and PC, that is the program counter. The ALU gives an output that is written into the data memory. Firstly, the content that the CPU will write into the data memory would be needed to specify in order to do so. Secondly, the address of the write operation. Thirdly, the output that will allow the CPU to write into the data memory. Lastly, the program counter holds the address of the next instruction, which follows the fetch, decode, and execute cycle. Now we have got an idea about the inputs and outputs of the CPU, so we can now move ahead with the HDL code of the Hack computer. This is the code which was provided in the task resources, and I will try my best to explain it as I go with the flow of the code. I have also added comments in the code in order to make it more understandable. In the starting of the code, the lines specify the interface of the Hack CPU, which consists of the chip name, that is CPU, and the input and output pins as explained before. The input and output pins correspond to the design of the Hack CPU. Now, moving on to the part section of the HDL code. First part of the code has three gates: NOT gate, AND gate, and mux16. These allow the CPU to perform special functions and specified operations. There are two types of instructions as discussed before, namely A and C instructions. In the first line of the code, using NOT gate, we will get to know if the instruction coming from the instruction memory is an A instruction or not. Firstly, the CPU will decode the 16-bit instruction coming from the data memory into a single bit opcode and 15-bit value. If the operational code is 0, then the instruction is an A instruction. Otherwise, if the operational code is 1, the instruction is a C instruction. If the instruction is an A instruction as determined by the NOT gate, then the specified 15-bit value is stored into the A register. But if the instruction is a C instruction, then it goes to the ALU, where after performing the necessary computations, the ALU output is fed to the A register. Next, AND gate is used in the code to determine whether the instruction is a C instruction or not. A 16-bit multiplexer is also used to select whether the ALU output should get stored into the A register or not. In the next part of the code, we have an OR gate. Load bit in the A register would be 1 if either the A instruction or the ALU output is fed to the A register. Next, A register takes the output A register in from the multiplexer and output load A as its inputs. It has A out, which is used in generating the value inside the A register. Then the MUX16 takes the output A out from the A register and in M, which is the currently selected value in the data memory. Then it selects whether A or M would be fed or loaded in the ALU, which would depend upon the 12-bit instruction value. Further, AND gate is used, which decides whether the ALU output should be loaded inside the D register or not. Output will only be loaded if both the parameters or both the conditions will be true, that is, the instruction is a C instruction and the fourth bit of the instruction is active. Next part of the code contains the ALU, which performs the computation part. It computes based on two inputs, which can be the values from the D, A and M register. It has 6 control bits that are ZX, NX, ZY, NY, F and NO that indicate which function will get computed to get the desired output. It provides the output ALU out as a result of the computations. It also has two output pins, namely ZR and NG, which determine the property of the result. If the output is 0, then ZR is set to 1, and if the output is less than 0, then NG is set to 1. Further, we have two OR 16 gates and one AND gate, which are used to determine whether the data is to be written inside the data memory or not. The first OR 16 gate gives the address of the RAM location, and the second OR 16 gate provides the value that is to be written at that particular location. AND gate is used to write the output only if both the input conditions are true. Next, we have used the AND, OR and NOT gates to determine the jump conditions of the program counter. The jump bits and ALU output determine the PC's load bit. These code lines determine the jump instructions, check the ALU output and determine whether the conditions are met or not. Therefore, the PC will be loaded with a value that will ask the CPU to jump to a specified instruction if the instruction is a C instruction and the conditions are met. However, PC is incremented by default if PC is not loaded. So this is how the CPU and its HDL code works. Thank you for watching.